Okay, so you're looking at the bottom of page 9 here, and we just finished example 10 where we were finding the kinetic energy of each of the three objects. And now for a quick review of the families of units. So I went ahead and wrote all of these in so that you can start writing them, save us all some time on the video. We have three families of units. There's the metric MKS, which is meters, kilograms, seconds. Then it also has force or weight. These are, weight is a force, in newtons, and energy in terms of joules. There's the metric CGS unit system, which is more common to chemistry than physics. Distance is centimeters, mass grams, times seconds. Force or weight is a new one that we don't really use in physics, and that is the dyne, and energy, the erg. Then there's the American FPS system, foot, pound, second, and this is one that we don't really work with much in this class. Distance is a foot, mass is a slug, time in seconds. Force and weight are both measured in pounds. And lastly, energy in terms of foot-pounds. But in physics, this is the system that we tend to use. Now at the top of the next page, this one accompanies a demonstration with a Newton's toy. And you're probably familiar with this, just maybe not by name. So there will be some sort of a little stand type thing, and it'll have probably 5 balls, and they are suspended something like this. And when you pull one of them back, it swings in and hits, and the one on the far end comes out, and it swings back and forth. And that is the Newton's toy. Since you're not seeing the demonstration in class, I'm not going to go through this too much. It's up here in case you want to write it down. A little bit more complicated math than most of the things in this class. But basically you have 2 of these balls, so you can move some out of the way so that only 2 are swinging. And so in the before, there is a steel ball at rest, and it's struck by another one of these balls in a perfectly elastic collision. Now, we know this one is at rest, and we know this one is moving, but that's about it. We know they're identical. That means their masses are the same, so they can both be represented by m for mass. And since we don't know this, I'm just going to call it v. This is the velocity as it comes in. So then we're looking to find the velocities of the 2 balls after the collision. And this is a perfectly elastic collision, which means that they're going to bounce apart. And so I'm not really sure what the speed of the original ball is, and I'm not really sure what the speed of the originally not moving ball was. But I can be pretty confident that they're not going the same speed since they hit and bounced apart. And so using the law of conservation of momentum, we were able to divide out mass from everything and find that velocity is x plus y. So then we use the law of conservation of kinetic energy, and you can take a 1/2 m out of all of these and end up with velocity squared equals x squared plus y squared. And this is where it turns into a math type question of solving a system of equations. So using this equation that we found, you can put in this one. So I solved it for y, and I replaced y in this equation. And then we just started solving things through. So here we simplified and then we found this, and we're here. And we found that x could be one of two things. It could be 0, or it could be v. So if x equals v, then y equals 0, and that means you missed, because this one should be moving. If it still has no speed at the end, it means it didn't get hit. If it gets hit, it's going to have some sort of velocity. On the other hand, if v equals y, so if x equals 0, that's a hit, and y equals v. And so the moving ball comes in, hits and stops, and the stationary ball takes off with the same velocity that of the ball that hit it. And you've seen these before, so you have an idea of how it works. Now you have some numbers to support it from a physics point of view. Does it accurately predict what you see? Yes. So this is a great way to see the law of conservation of kinetic energy. If you pull back two balls and release them, then two balls swing out to the other side. And again, energy before equals the energy after, because the kinetic energy is being conserved. If we pull back and release 3 of the balls, then 3 of the balls swing out to the other side. And in this situation with the 3 and 3, that means the center one is going to be pretty much constantly in motion. So these 3 would swing out and back, and then these 3 would swing out and back, and then these 3. So the middle ball is going to be constantly going back and forth because of the amount of energy. And it'll be the same if you had 4 balls pulled back for the start. Example 12, 2 balls meet head-on in a perfectly elastic collision. So I've already got my picture here. Ball A has a mass of 20 kilograms and a velocity of 6 meters per second. Ball B has a mass of 10 kilograms and a velocity of 15 meters per second in the opposite direction of ball A. So when you're looking at this 15, it says in the opposite direction, that's your cue to put in a negative sign. If they have different directions, they have different signs. So find the velocities of the 2 balls after the collision. And here I have my after conditions. Here's the 20 kilogram ball, and here's the 10 kilogram ball. And their velocities are x and y. In my picture, these balls are both moving off to the right. Doing that makes this a positive x and a positive y. So at the end, I don't have to worry about flipping signs or whatever. But just because my picture indicates that these are going right doesn't mean that my numbers will support it at the end. It just makes the drawing easier to use. So we're going to look at this one. So I said find the velocities of after the collision. And so this is going to require us to do something similar to example 11, where we use both the law of conservation of momentum and the law of conservation of kinetic energy. So here is the law of conservation of momentum. And we'll go ahead and fill in our numbers. I'm going to leave off the units just for space here. Mass of ball A is 20, velocity is 6, plus mass of ball B is 10, velocity is negative 15. Mass of the first ball is 20, it's new velocity, not sure, x, plus mass of the second ball is 10, new velocity is going to be y. So simplify a little bit. Can divide all of these by 10. And so -3 equals 2x plus y. And this is really about as simple as we can get it for now. So we need to also look at the kinetic energy side of things. That's over here. And that is 1/2 mv squared for each of these. Here's ball 1. This is the kinetic energy of ball 2 before. Here is ball 1 after, and ball 2 after. Again, filling in our numbers. Some simplifying here. 360 plus 1125. It's positive because you're squaring the -15. The negatives can disappear. And we've got 10x squared plus 5y squared. So take a 5 out of everything, and we end up with 297 equals 2x squared plus y squared. And where we are, these two things are as simplified as they can be. Until now, we get to this point where we want to solve this system of equations, and the easiest way to do that is to solve the momentum equation for y. And so y equals -2x minus 3, and we take this and replace it for y in this equation. 297 equals 2x squared plus, and here we have -2x minus 3, and that's a quantity squared. So we are solving this, and at the same time simplifying. So I'm going to subtract 297 over. I'm going to put these together. And it looks to me like you can take a 6 out of both of these. If you check your calculator, same for this one. And so x squared plus 2x minus 48. And this is solvable. So x minus 6 and x plus 8 equals 0. And so you get two numbers. You get x equals 6 and x equals -8. So looking at this, x equals -8. So we have this ball A, ball number 1, coming in and hitting, and what we expect in this Newton's toy is for it to rebound in the opposite direction. And so if it's 6, if it continues in the same direction with the same speed, this one's a miss. And so this is not a good answer here, because if the speed here is the same as it was originally, it means the two balls did not actually collide. But if it goes off at -8 meters per second in the opposite direction, this is likely going to be our speed. So we're going to put this one in over here. So y equals -2 times -8 minus 3. And so y equals 13 meters per second, and x was -8 meters per second. And of course, the signs give us the idea of the direction here. This one, if you wanted to write it out, it'd be ball B goes off at 13 meters per second in the original direction of ball A. And this one, ball A goes off at 8 meters per second in the opposite direction of its original, something like that. It's going to be wordy either way. This last one, example 13, is a math proof. It says, show that this collision is consistent with both the law of conservation of momentum and the law of conservation of kinetic energy. A ball is hit by another of 3 times the mass, twice the velocity, traveling in the same direction. So I've already got this set up. A ball is hit by a ball of 3 times the mass and twice the velocity. After the collision, the large ball continues in the same direction at a velocity of 3/2 the original velocity. While the small ball's velocity increased to 5/2 of its original value. So step 1 is draw a picture here, and I've got that set up already. And this is a show that we're using the law of conservation of momentum. And we're plugging in our numbers. So ball 1, 3 times the mass, twice the velocity. And this one's just m times v. Mass is still 3 times the mass, and the velocity is now 3/2 times v. Mass m and 5/2 v. There's a lot of simplifying to be done here. 6 mv plus mv equals 9/2 mv plus 5/2 mv. And so add these two together, that's 7 mv equals, and 9/2 plus 5/2 is 14/2, which is 7 mv. And this one checks out. Then the conservation of kinetic energy. So we're going to do the kinetic energy version of this one. Move this up. Same basic type of formula, but we're using kinetic energy, which is 1/2 mv squared. Get some more over. And again, putting in all of the numbers that we have, 1/2 mass of ball A is 3m. This one is 2v squared, quantity squared. 1/2. That's m and v quantity squared. Some simplifying, and we end up with, this is 6 mv squared. This one is 1/2 mv squared. Over here, 27/8 mv squared plus 25/8 mv squared. So solving this comes out to be 13/2 mv squared, and on this side 52/8 mv squared. And 52/8 simplifies. So 13/2. So this one checks out too. And so show that momentum is conserved, yes, and show that kinetic energy is conserved, yes, it is.